We lock down our systems with complex algorithms and layers of encryption, assuming that if the software code is sound, the device is secure. But code does not execute in a vacuum. It runs on physical hardware. Microcontrollers execute instructions sequentially through physical execution units. Every time an instruction passes through these units, transistors open and close, drawing varying amounts of electrical current from the power supply over time. By mathematically subtracting a trace of a loop running n-1 times from a loop running n times, ambient noise cancels out. The remaining isolated power spike represents the exact current drawn by a specific hardware action, like an add R0, R0 instruction. By identifying the unique power signature of every instruction, reverse engineers can map a physical trace directly back to the software. This vulnerability extends to cryptography. In a differential power analysis attack, or DPA, attackers feed varying inputs into a device and statistically analyze these power traces. By observing how power consumption changes based on data being processed, they extract secret encryption keys bit by bit. To understand why this happens, we must look past the macroscopic circuit board and travel down into the microscopic architecture of the silicon die itself. While software-level countermeasures like shuffling or masking can introduce algorithmic obstacles, they do not change the underlying physical behavior of the gate. As long as the logic gates themselves broadcast their state to the power supply, the physical foundation of the system remains transparent to an attacker. This standard static CMOS logic gate is modern computing's baseline and the root of power leakage. Processing binary data triggers 4 state transitions. Static transitions, holding a 0 or 1, require minimal energy. But dynamic transitions, switching states, asymmetrically charge and discharge capacitance, creating distinctly different power spikes. This physical asymmetry means that every logic operation generates a deterministic physical signature. The data being processed dictates which transition occurs. The transition dictates the shape of the power spike. Therefore, the data is entirely visible to anyone measuring the current. Standard CMOS architecture cannot protect cryptographic keys. Securing an embedded system requires engineering a new way to compute logic in silicon. The first theoretical approach to solving this physical vulnerability is known as hiding. The engineering objective is to enforce a perfectly constant power consumption, regardless of the data passing through the gates. To achieve this, engineers developed a hardware countermeasure called Sense Amplifier-Based Logic, or SABL. SABL uses dual-rail outputs. Instead of computing a single result, the gate simultaneously computes the true mathematical function on one rail and its exact inverse complement on the other. SABL dictates a strict 2-phase clock system. The first cycle is the pre-charge phase. A clock signal resets both the outputs to a known, identical high-voltage state, flushing out any previous data. Then comes the evaluation phase. Input data flows into the differential network, and exactly one of the 2 output rails fires. Because one rail always discharges while the other holds, the gate charges the exact same load capacitance every single clock cycle. If the gate pulls the exact same amount of current to process a 1 as it does to process a 0, the resulting power trace is perfectly uniform. The attacker is left staring at identical spikes. In theory, hiding severs the correlation between data and power by forcing absolute, unyielding physical symmetry. But theoretical mathematics and actual semiconductor manufacturing operate under different rules. At the nanometer scale, perfect symmetry is impossible to manufacture. When fabricating the microscopic physical wires attached to the dual rails, one wire will inevitably be slightly longer or thicker than the other. This creates a capacitive mismatch. Because the parasitic capacitance on the rails is no longer identical, the power trace diverges. The gate draws slightly more power to drive the thicker wire, exposing which rail fired, and once again revealing the data. This physical imperfection introduces a temporal vulnerability, known as the early evaluation effect. In a complex circuit, logic gates are cascaded together in long chains. If input signals arrive at a gate at slightly different times due to routing lengths, the gate evaluates its output at different times. These staggered arrivals cause a cascading delay, creating a clear dependency between the input data and the exact timing of the power spike. Engineers try to mitigate these imbalances using massive layout overheads like back-end duplication and fat wire routing methods. They manually force parallel routing to match wire lengths as closely as physics allows, ballooning the physical size of the chip in the process. Even with these heavy interventions, hiding ultimately fails against high-resolution differential power analysis. Human manufacturing simply cannot achieve the flawless physical perfection required to silence the leakage. An alternative to forced symmetry is deliberate randomization. This design strategy, known as masking, does not try to equalize the power trace. It aims to make it unpredictable. A primary gate-level masking implementation is random switching logic, or RSL. Looking at the schematic for an RSL NAND gate, you have standard data inputs alongside an enable signal and a dedicated random mask input. RSL employs Boolean masking directly at the gate level. The true binary data is processed alongside a stream of randomized Boolean variables fed through the mask input. This extra variable divorces the physical state of the transistors from the underlying unmasked data. The transistor paths shift and fire unpredictably according to the mask, even if the actual data inputs remain perfectly constant. To an attacker monitoring the current, the resulting power trace registers as uncorrelated noise. The repeating patterns tied to the input data are buried. But RSL introduces severe architectural costs. It absolutely requires an external random number generator running constantly to feed the mask, and a global enable signal to time the logic evaluations, both of which cripple the maximum operating frequency of the chip. While masking successfully bypasses the need for physical silicon symmetry, it shifts the engineering burden directly onto complex architectural overhead and severe performance degradation. DPA resistance is a strict economic trade-off. It is bounded entirely by the physical limits of a chip's available silicon area and power budget. This scatter plot evaluates countermeasures, area delay product on the x-axis versus security on the y-axis. Standard CMOS establishes our baseline at the origin. Pure hiding techniques like SABL illustrate the cost of hardware security, requiring massive leaps in physical area for only moderate security gains. These hiding techniques plateau on the security axis precisely because of the capacitive mismatches and routing imperfections we examined earlier. To push past that plateau, engineers developed hybrid logic styles like masked Sable. By combining the dual-rail equalization of hiding with the randomized noise of Boolean masking, it achieves the highest possible security. Masked Sable plots in the extreme upper right quadrant, representing maximum protection and maximum overhead. There is no cheap patch for side-channel leakage. Achieving a truly leak-proof logic gate demands exponential increases in silicon real estate and power consumption. Stepping back from the microscopic gate level, we can see the macro architecture of a complete system on chip. Implementing masked Sable across an entire microcontroller is economically and physically unfeasible. The sheer size and power requirements would render the device unusable for standard operations. Instead, chip designers utilize a cryptographic boundary strategy. These extreme logic styles are surgically deployed in tiny, isolated sections of the chip, tasked only with executing the most sensitive operations, like AES encryption blocks. Standard, unprotected software instructions will always broadcast their secrets to the power supply, but with highly targeted hardware engineering, it is possible to physically sever the link between the data being processed and the electricity consumed. Hardware security is a direct trade-off. To eliminate the physical signature of a computation, the cost must be paid in raw silicon and power.